So welcome to the seventh week of the linear dynamical systems. So in this week we will discuss about the observability and minimal realization problem. So the outline of this week is we will start with the concepts of observability and its tests. Then we will discuss about the Kalman decomposition, which will include the controllability and the observability analysis and combined. Third, we will see the weaker concept, then observability, that is detectability, and we will also see the test. And finally, we will conclude with the minimal realization. So, observability is basically related to the problem of the controllability, what we had discussed in the third or fourth week. So, if you recall the problem of the controllability, we want to ensure that whether there exists a control law such that I can steer my state trajectory from some x of t naught to some x of t1. Okay, so here let's say if a continuous time LTI system is given by A, B, C, D matrices where x is n dimensional, u is k dimensional, and y is m dimensional. So we know that if the pair A, B is stabilizable, then there exists a state feedback law which is given by u is equal to minus k times x, which we have defined as control law, that asymptotically stabilize the system, this one, that is for which this matrix A minus bk, which is the closed loop matrix, is a stability matrix. Okay, now if the pair AB is controllable, then we can achieve much more performance specification by designing this state feedback gain matrix K. Okay, now here you would see that for computing the control law U, you need the information of the state signal. So however, when only the output Y can be measured as opposed to the whole state X, the control law cannot be implemented, right? Because if you do not have the direct measurement of the signal X and you only have the direct measurement of the signal Y, then you cannot implement this control law. You need the information about the state signal. So possible solution, in principle this difficulty can be overcome if it is possible to reconstruct the state of the system based on its measured output and perhaps also on the control input that is being applied. Okay, so the idea here is now the only measured signal in this system is the external signals, which we have defined earlier as the input to the plant and the output of the plant. X is an internal signal, right? So now if it is possible to reconstruct the signal X based on the available measurements U and Y, then it would be still possible to use this control law. Okay, now there are other ways of constructing this X also. Trivially speaking, now see the output equation. The output equation is given by y is equal to cx plus du. Okay, the signal u is already a measured signal, so I can take this du onto the left hand side. So let's say y minus du is equal to cx, and let's denote this y minus du because d matrix is known to me, u signal I am measuring, and similarly y, so I can denote this as some y tilde is equal to cx. Okay, now if C is invertible, that is to say if the inverse of the C exists, then I can perfectly reconstruct the signal X as C inverse times y tilde. Here the information of the matrix C is also known to me. Y tilde I have computed by the signals Y and U. So if C is invertible, that is the inverse of the C exists, then I can directly compute the signal X. Okay, but this is only possible if the number of outputs is equal to the number of states, right? The first restriction is that C should be a square matrix, and the square matrix could be possible if we have the number of output as equal to the number of states. But when the number of outputs is strictly less than number of states, which is always possible, or which is mostly possible, the instantaneous reconstruction of X is not possible, right? But it may still be possible to reconstruct the state again by taking the signals Y and U over some time interval T0 to T1. Yeah? So this you can visualize this. Say for example, if we many times we have considered a single input, single output system, which is of some ratio of polynomial numerator and denominator. Okay, which is nothing but y of s and u hat of s. Here we know that the output is 1 and the input is also 1. Now depending on the degree of the polynomial of the denominator, we have so far seen the dimension of the state matrix, A matrix. So if let's say if ds is of some the degree of the polynomial of ds is 3, then in that case we would have the number of state variable as 3. Okay, but we know that the output is 1. So in that case we cannot have the invertibility of the C matrix. But what we want to know that whether it is possible by collecting the signals y and u, we can construct somehow this x or not. Okay, so in this week we will study some conditions, that under what conditions we can say that we can reconstruct this signal x. How we will going to reconstruct it, we will discuss this in the last week of this course. So before proceeding forward, we will use two formulations. One is the observability and second is the constructability. The observability refers to determine the initial condition of the state at T0 from the future inputs and outputs ut and yt observed at or during the interval T0 to T1. Okay, so let's talk about the time axis. So this is T, this is T0 and this is T1, and here we have taken T1 greater than T0. Okay, now let's say between this interval we have observed the input output signal, right? So using this information of input output signal, if I am computing the value of x at T0, then we call it the observability. If we are computing the value of x at T1, we would call it the constructability. Okay, so then we define the unobservable subspace similarly to what we have defined during the controllability week, where we have defined some subspaces and then did some characterizations. So consider the continuous time linear time varying system where now all ABCD matrices are time varying with the same dimension. So we know that the system state x0 defined as x at T0 is related to its input and output on the interval T0 comma T1 by the variation of constants formula what we had seen in the first week. This is the solution of the LTV system. Yt is equal to C of t times state transition matrix phi x0 and this integrand plus dtut. Okay. So to study the system's observability, we need to determine under which conditions we can solve this equation. So this equation is similarly to what we had seen earlier. So this is the solution, right? Now if you pay attention to this term, in this term you have information of all the signals and the functions. U, we are measuring the signal. B, phi and C you can compute depending on the system matrices. Okay, similarly here we know about U and D is already known to us. So if I take this complete term again onto the left hand side and defined as y tilde, which is yt minus this whole term for all t during this interval T0 to T1, I can specify it as y tilde is equal to C into phi into x0, where C is my output matrix and phi is the state transition matrix, right? And I want to find out x0, say for example. Okay, again I cannot take the inverse of this part because I know phi is non-singular and a square matrix, but since it is being pre-multiplied by the output matrix, which is still possible that it could be a non-square matrix. So the overall matrix here would still be non-square, and I cannot take the inverse of this one to directly compute this x naught. Okay, but we will see some spaces, some subspaces, and for which we can characterize that for what, or for what elements x naught the uh, we can construct this signal. Okay, so the first of all we will define unobservable subspace, that given two times t1 greater than t naught, which is greater than equal to 0, the unobservable subspace on t naught to t1 we denoted by this calligraphic u and o, unobservable t naught comma t1 consists of all states x naught for which this condition is satisfied. Right? So there is a direct implication from the previous equation by which we can define the unobservable subspace. So let's see. So this is the equation we had seen earlier. Y tilde is equal to C phi into x naught. Okay. Now if my y tilde, which is basically the subtraction of the output and a function containing input, if this subtraction becomes equal to 0, then all those x naught would becomes the what would belong to my unobservable subspace, because I cannot observe them at all. Right? So this is what this definition says, that if the C phi x naught becomes equal to 0, then all those x naught for which this equation is satisfied would belong, or would make me or would give me the unobservable subspace. Okay. Now let's see some properties of this unobservable subspace. So suppose we are given two times, again t1 greater than t0, and an input output pair uy over this time interval t0 to t1. Now when a particular initial state x0, that is x defined at t0, is compatible with the input output pair, then every initial state of the form, so you can define this as x tilde, that x tilde is defined as x naught plus xu, where xu belongs to that unobservable subspace, right? So is would also be compatible with the same input output pair. Why? Because say for example x naught belongs to that input output pair, then it means that y tilde won't be 0 for x naught. So I can write y tilde is equal to c into phi into x naught, and since xu belongs to the unobservable subspace, it would have I would have 0 is equal to c phi times xu. So if I sum these two equations, I would get y tilde is equal to c phi x naught plus xu. So I cannot differentiate, or I mean to say this one would also belong to the same input output pair. The second property, which is the most important one, again consider two times t1 greater than t0 and the input output pair uy over this interval. So when the unobservable subspace contains only the 0 vector, then there exists at most one initial state that is compatible with the input output pair. Right? So because of this property only, it is possible to uniquely reconstruct the state of an observable system from future input and output. Let's see. So consider two different states, x0 and x0 bar, okay, which are compatible with the same input output pair. So I can write the same equation for x0 and x0 bar, right? Subtracting these two equations, I would get 0 onto the left hand side and c phi times x0 minus x0 bar. Now this equation means that this x0 minus x0 bar, which is not equal to 0, belongs to the unobservable subspace, because this equation has been satisfied as we have seen the definition. So there exists at most one initial state. There cannot exist two initial states, right? So that is why it helps us to uniquely reconstruct the state of the system. So the above properties motivate the following definition. So given two times t1 greater than t0, the system, continuous time, linear time varying system, is observable whenever its unobservable subspace contains only the zero vector, right? Meaning to say that there does not exist x naught for which that previous equation is satisfied, right? So the matrices B and D, we had seen that they do not play any role in the definition of the unobservable subspace. So we will generally talk about the unobservability or the unobservable subspace or observability of this system, or let's say the pair A comma C, okay, which we define pair AC of CLTV. Now similarly we can define the unconstructible subspace. Now here we had seen only the value of the state at some particular time. Based on that we have defined the unobservable and unconstructible subspaces. So here the future system states x1 defined as x of t1 at time t1 can also be related to the system's input and output on the interval by the variation of constants formula by using this one. The only difference is that instead of t0 now we are having t1 at every places, okay. And by keeping the same definition, that the unconstructible subspace on the time interval t0 to t1 consists of all states x1 for which this equation is satisfied. Again, the differences of the t1 and the value of x at t1, which we have defined as x1, okay. So all those x0 would belong to the unobservable subspace if this equation is satisfied for some x0 with phi t comma t0, and now for all x1 and phi t comma t1 if this equation is satisfied, then we call it the unconstructible subspace, okay. The property would remain the same, that when a particular final state x1 is compatible with the input output pair, then every final state of the form x1 plus xu, because x1 is compatible and xu belongs to the unconstructible, so the summation of that would also belong to or would be compatible with the same input output pair, right? Second, when the unconstructible subspace contains only the zero vector, then there exists at most one final state that is compatible with the input output pair, and this ensures the uniqueness also. So if we talk about now the system, the constructible system, that the system is constructible whenever its unconstructible subspace contains only the zero vector, that is UC is equal to 0, right? That there is no element in that subspace. We can see one example. Let's talk about the parallel interconnection. So this is one system, let's call it system 1, and this is system 2, and we are supplying the common input to both the system and taking output as the summation of y1 plus y2. So you can represent this parallel interconnection by using this combined state space equation, where x is x1 and x2 and a1 a2 would be in the diagonal elements, and b1 b2, and this would be u, which is missing, okay, and y is equal to c1 c2x, right? So the output you can also write by computing y1, which would be the y1 of this system and y2 of this system, and I can sum them up to compute y, and you can write it as c1, it should be this c1, and this integral is y1, and this should be c2, so this and this would be your y2, right? Now suppose if your c1 and c2 become equal to c, and a1 and a2 become equal to a, then this complete equation I can write this as this one, okay. And you would notice that by knowing only the input and output, we cannot distinguish between the initial states for which x1 of 0 plus x2 of 0 is the same, right? Whatever I would compute, let's say all the conditions of the observability has been satisfied, and I have been able to compute this x, but that x would be the summation of both the states, and the concept of observability says that I need to know x1 and x2 individually, right? And here I am getting the summation. So this, whenever you are having this parallel interconnection, the system might not be observable always. Okay. So similarly to what we had seen during the controllability week, that we had introduced the gramians and we did the characterization of the discussed subspaces using those gramians. So first of all, we will define the observability and the constructibility gramians as that given two times T1 greater than T0, the observability and constructibility gramians of the system are defined by this WO and WCN over T0 to T1. Okay. So this here phi is the state transition matrix, C is the output matrix, and yes. So both gramians here are symmetric positive semi-definite square matrix of dimension n. Right. So based on this gramians, we can give our first results, which basically characterizes these subspaces. So the first trivial method is to find out all those x naught for which the previous equation is satisfied, that is C phi into x naught is equal to 0. Now if you want to characterize the entire subspace, that subspace is basically given by the kernel of the the observability Gramian matrix WO. Okay. Similarly, the unconstructible subspace is equivalent to the kernel of the constructibility Gramian WCN. Okay, we can see a quick proof. So from the definition of the observability Gramian, we can write it in the, first of all, we can write it in the quadratic form as x naught transpose WO into x naught, and then substituting the value, the matrix WO here, I would get this one, and then using the property of the norms and the quadratic forms, I can compress this long expression into the squared norm of this term. Okay. So this is basically C phi x naught, and this is the transpose. So I can write it the squared norm of this term. Right. Now let's see, because now we want to show that if an element belongs to this unobservable subspace, then that element would also belong to the kernel of the observability Gramian. Okay. So let's see. So therefore, x naught belonging to the kernel of this WO implies, so if you remember that if an element belongs to this kernel of any matrix A, then it means that A of x is equal to 0. Okay. So if x naught belongs to this kernel of WO, then what would happen? WO x naught would be 0. Now WO x naught, if I put WO x naught 0, then this left hand side term would become equal to 0. Right? Now if this term becomes equal to 0, and this is the integral of the squared norm, and this would be only 0 if this inside the norm is itself equal to 0. So this implies that x naught belonging to the kernel of this observability Gramian implies that this term would be equal to 0. And by taking the definition of the unobservable subspace, that all those x naught would definitely belongs to that unobservable subspace. So all those elements which belong to this subspace would definitely belong to this unobservable subspace, meaning to say that this equivalence is satisfied. Okay. Now see the reverse one. Now if we have x naught belonging to the unobservable subspace, meaning to say this equation would satisfy. Right? Now if this equation is satisfied and I put it here, it means the quadratic form itself is 0. Now if the quadratic form itself is 0, it implies that this is equal to 0. Now there is under some condition this implication would hold. That is to say that satisfying this one, implies x naught would belongs to the kernel of this observability matrix, and this is only possible because W is a positive semi-definite matrix. Now if W is some non-semi-definite matrix, then this implication won't hold. Okay. So a similar argument can be made for the unconstructible subspace.